And the simple rule that allows me to only investigate one of the subtrees is that, okay, we're talking about binary search trees. So the way it's organized is that if my values that are stored in the tree can be compared to each other, so it's just integers, I'm storing a load of integers, then I know I can organize it so that, oh, that's nice, it's like a cinema where you can sleep. I know that, I need some light on myself. Follow my eyes. I know that if the value I'm looking for, if I'm at a node and it's sourced, let's say 10, and the value I'm looking for is actually less than 10, I need to go to the left subtree. So if I can organize the tree so that all the smaller values are on the left subtree, that will make me very happy, because then I have symbol tables. Let's have a little picture. There we go. So I'm at this node. In this case, they're storing keys and values, but let's forget about the values for now. Let's just sort of think about keys. If I'm looking for the key 10, and it's not in this node, then I'm actually currently at this. Currently at. And I know that all the smaller keys are in the left subtree. I'm looking for a smaller key than this one, less than 10. I know that all the less than 10s are in the left subtree. I only need to search in the left subtree. I have all the greater keys in the right subtree, so I don't have to search this. If I'm looking for 5, and I see on a node that contains a 10, I only have to look at the left-hand subtree. It won't be here, because these values are only the ones that are bigger than 10. So it's an amazing little, just this one little scheme that makes life a lot easier. And how much easier does it make life? Let's say I have a tree with 1,000,000 nodes. Now, if I didn't have this organization, I would look at this node, and then look at its left subtree, where I'd look at all the nodes. And then, if I didn't find it yet, I'd have to look at the right subtree and look at all these nodes. I'd have to look at every single node to see that there is no 5 in the whole tree. That means I'd have to look at 1,000,000 nodes. Let's make an assumption that we can kind of enforce, we won't do it in this course, but we can enforce that these subtrees are equally sized, or at least roughly equally sized. So that we say the tree is balanced. There's a balance between the left subtree and the right subtree. If we can do that, I look at this one, it's not the 5 that I'm looking for. Now, I only have to look at the left subtree. So I've looked at one subnode out of 1,000,000, one node out of 1,000,000, and I'm going to investigate the left-hand tree, which only contains half the nodes, because the tree is balanced, the other half is sitting on the right-hand side. So I'm only going to look at 500,000 nodes. I'll look at the parent. If I don't find it, I'll go to one of the subtrees, and it will contain 250, and then 125,000, and then how many? 87,500, and then divide that by 2, which I won't do now. I won't tell you 35,250. Leave that to you. So every time I half the number of nodes that I have to look at, every time I go to the subtree, it's only half as small as the whole tree. So that means I'm dividing by 2 every time. Essentially, I'm calculating the log base 2. So if I can enforce the fact that the trees are balanced, which I can, but won't. But if I can enforce the fact that the trees are balanced, all trees are balanced, it means I only have to look at log n. N is the number of nodes. So before I had to look at all 1,000,000, that's order n keys I have to look at. Now I only have to look at log n. That's an amazing savings. So for 1,000,000, I only have to look at 10 nodes. You've done this before, haven't you? I can see it in your little beady eyes. Any girls? None? Mom? I'm astounded. This is the book. So I'm going back in time. We're going back in a journey in time, past list, stacks, and queues, to a chapter I like to call searching and searching and sorting. Sorting and searching, that's right. No, that's crap. No. Merge sort, no, I don't want to sort, I want to search. binary search. What did we do in binary search? We had an array that was sorted, and in this case, being balanced. Well, remember the little tree I had? Being balanced is somewhat equivalent to being sorted. In that case, you had a sorted array, and you look in the middle node, which is kind of like my root of my tree, and then you check, is this a key I want? A key I'm looking for is smaller, I would only look at the left-hand side of the array. Do you remember that? No. You're all zombies. You don't remember anything. Do you remember that? Were you in class? Don't remember if I was in class. Amnesia. It happens to basic people, don't be ashamed. It's not a shameful disease. Mass amnesia, it happens. It's highly contagious, and it's fine. I'll tell you what you need to remember. You need to remember that you're a very good student at the Supreme University, studying very hard, especially like computer science, and plan to make it your career. And 2 weeks ago, 4 weeks, 5 weeks ago, you looked at binary search. And in binary search, we have an array that's sorted. You're looking for an element, you look at the middle one each time, and then based on that, you decide to go look at the left-hand side or the right-hand side. Every time we halve the number of keys we have to look at, that's the same as taking the log. If you repeatedly halve. Do you believe me? Or do you think I'm talking nonsense? What is the log of 1 million? Base 10. 6. How did you get 6? Okay. Now, I fortunately think of the number which you don't know what cows is. I'm not going to do that. I'm not going to roll fast. The way to primitive people, before humans even, the Homo erectus, the way they calculated logs was to take a big number like 1 million and dividing it repeatedly by 10. So 10 goes into 1 million once, 100,000, twice 10,000, 3 times 1,000, 4 times 100, 5 times 10, 6 times 1. So 10 can go, if I repeatedly divide, 10 can go 6 times into 1 million. So 1 million is 10 to the 6. So we'll multiply them after and get back to the million. And that's a log of 1 million base 10. Same way, if I repeatedly divide by 2, I get something. You know, I'm not going to tell you what I get, but no, I'm telling you, it's pretty huge. It's pretty large, big. Okay, way too far. Let's get back to binary search trees. Oh, there's a nice tree. No, it's not. Okay, fine. 650. Oh, you all understand binary search trees, don't you? My brilliant explanation powers of explanation has convinced you that a binary search tree is a good thing, and we want to construct one, and especially we want one for our symbol table, because if we sort this binary search tree, sort it, balance it by the key, we can very quickly look up a particular key in the symbol table, in the binary search tree, and then I can determine, is the key value mapping that I'm looking for in the symbol table or not. So that's hunky-dory. We don't have an issue with that. We can even use recursion. Let's find the routine that recurses. Get. Let's have a little look here at get. What does get do? It says this. This is code inside my symbol table implementation. This time it's a symbol table that uses a binary search tree. So it's a little confusing because symbol table is ST, binary search tree is also BST, so it's a little confusing, but basically I think this stands for B, binary search tree, and implicitly it's a symbol table. So I define a private class node that has a key and a value. A key and a value. So that's for storing my key that I'm mapping to a particular value. And a left and a right. And these are both instances of node. So the references to an instance of a node class. They're basically pointers to the two nodes that are at the top of my left and right subtrees. And if one of them is null, both of them is null, neither, that means that subtree is empty. There's nothing there. Okay, then there's a little constructor that simply puts key in the key field and value, value in the value field. That's fine, we can live with that. And then we have a routine called get. That's one of the routines that's specified in the symbol table interface in the contract. So we must implement it. It takes a parameter of type key and it returns a value. It's going to return the value that this key is mapped to, or null is there null. So it must return null if there's no such key in my symbol table. But all this get does, a little confusingly, is to call a different get. And now it passes two parameters. It passes the root, so the very top node in my binary search tree, which is right there, the first field declaration in this binary search tree class. And it also passes key. And this get is going to do the real work. And it's all recursive, and it's beautiful, and you already understand recursion. So I'm not going to talk about it too long, but let's just have a look at it. I'm at node X. I'm looking for key. My first question is X null or not? Because if X is null, I can't even look at its key value. It means that I'm looking at an empty tree, a tree with no keys. So if X is null, I will have to return null. I did not find a key in this tree. So it says if X is null, return null. That's fine, that's not category. Then X is not null, so I'm actually at a node. I'm at, no, I'm going to change the page. I'm at a particular node. I don't have to change the page. You can all see here, I'm guessing. Thank you, thank you. Oh, I'm here all night, folks. Okay, right. So that confusingly says a big node is pointing to this thing, but this is an instance of a node. But let's say that's root or X. Let's say it's X. If X was null, I didn't find anything in trees empty, return null. X is not null, so now I need to look at this node, X. I need to look at its key. And if its key is equal to the key that I'm looking for, I found the key value mapping that I'm looking for. So I return the value that's inside X. Only thing is, I can't use double equal sign. I will have to use equals. And here I've used compare to, but well, they've done it differently. Let me write my way. It's a little bit of a pity, but don't mind that. Binary search tree simultaneous. Here we go. What do I need to do? It's going to implement my ST interface. Yes. Yeah. Ah, okay. It needs a comparable key. Okay. Never mind that. Just ignore that. Cliff is being funny. You need the key and a value, which I haven't specified. It's kind of saying I promise to implement a symbol table with key and value, but I haven't said what key and value is. So either I'm going to specify concrete types and say things something like this BST will implement strings mapped to doubles. Java will be fine with that. I was complaining that I haven't implemented all the methods that the contract requires, but Java's fine with the string double. But I don't want to limit myself. I really want to map any key to any value, and I need to somehow get them from somewhere. And where I get them from is here. I'm going to say a binary search tree symbol table also takes parameters. You also need to tell it what key, what's the key, and what's the value. And now it's complaining that key needs to be comparable because that's what the interface said. Do you remember? Of course you do. Key is something that extends the comparable interface. How do I fix that? Well, the way I'm going to do it, is to say, well, this key also needs to implement, extends the comparable interface. So when you instantiate BSTSD, you need to pass it two types, key and a value. And that key type needs to be an extension, it needs to implement the comparable interface. And it needs to be comparable key interface. It needs to be I need to be able to compare to other keys. I think that's probably a little confusing. If I have to guess, if I ask a question about that in the final exam, no one will get it right. Or maybe a few people. Oakley dokley. Right, let's just fill in the other stuff that I want. What did I have? I had a private node. That was my root. That's the root, but I haven't defined node yet. So let's say it's a private class. No one can see it from the outside, called node. It has a key field that's of type key. It has a value field of type value. It has a left. It has a right. And will I write the little constructor? Yeah, let's do that. Node, key k, value v. That's not key equals key. So I rename it. Why write k and v? This dot value equals value. Fine. Okay, right. So I have my little node class. All these are yellow because I never use it. I do use node, so that's identified, but I also never use root, so that's got a yellow stripe as well. Okie dokie. I'm not going to copy that code perfectly, but let's see. I'm going to put this stuff away for now, down below. I don't like that. Let's move put down a little bit. Yeah, there we go. Get. And what did we say we're going to do for get? Don't look at the other screen. It's all my eyes. We're going to call it a kind of internal get. It starts at the root and recursively tries to find that key in the tree. So I'm going to say return my own get, which starts at the root and looks for key. In fact, I want to call it key. Okay, I haven't written that yet, but one thing you must notice is that this root is no longer yellow, no longer yellow underlined. Java's not complaining that I'm never using it because I've just used it. And I'm going to write that routine. It's going to be private. Nobody needs to know about it. It's going to return a value because if I find the key, I'm going to return its corresponding value. Get, start at some node. I'll call it node. Take some key. There we go. Now Java's complaining it's not returning anything. So let's start the code. If node is null, this is an empty tree. You won't be finding value in here, so just return null. There we go. Java's still complaining because there's a way for this routine not to return anything if it just node is not null. I still need to handle that. So I'm going to say if node is not null, check its key value. Check the key value inside this. No, frozen the wrong one. But check the key value inside this node. And if it is equals to my key, then I've actually found a node whose key value is the same as the key that I'm looking for. So I'm going to return this node's value. Return node dot value. So this is when the tree is empty, and I'm return null. This is when there's actually a value there, and the key there, and it's the one I'm looking for. So I'm simply return the value. Found the value. Now the issue is, do I go to the left or the right? Because obviously this node is not equal to key, but it may still be in one of the subkeys. How do I decide if I go left or right? I compare the keys. I want to say something like, if key, the one that I'm looking for, is less than the key in this node, look in the left subtree. And otherwise, look in the right subtree. But I can't say this, because I can really only compare primitive types, integers, floats, bytes, short, longs, doubles, all those kind of things. Chars I can compare. I can't compare Booleans. I can't compare two things that are of type key, because I don't know what a key is. It may not have that. So that's why I need to compare to. I need to be guaranteed this key can be compared to other keys. This key value can be compared to other keys, because I now want to compare it to node.key. And I know that key implements the comparable interface, which means it has a routine called compare to. I can call that, just like I did in the textbook. So I can actually call it and say, if key dot compare to this other key is less than 0. I'm comparing key and node.key. And I'm using this compare to method, which is guaranteed to exist because key implements the comparable key first. If it's less than 0, it means that key is less than node.key. So I must go look at the left subtree. I'm going to use recursion to do that. I already have a routine almost completely written that checks if a key is in a tree. A key in a tree. So I can use recursion to say, okay, call this get, this very same get that I'm using at the moment, look at the left subtree of this node and look for key. And whatever you find in the left subtree, return that. So if you do find a key in the left subtree, this get will recursively return the value and send it back to me, and I'm going to also return it, all up the recursive chain. And eventually we'll get to that get, and that'll be the value it sends back. Are you comfortable with recursion? Okay, and people who are responding are nodding, so I'm going to assume you're all very happy about it. Okay. Otherwise, look in the right tree for key, leave that. So, first approximation is this is the routine I tried. The coding on this other screen in the book is just slightly different because I'm now comparing key and node.key once when I call this routine, but I'm also comparing them when I call equals. Because in fact, often equals is simply implemented like this. Public Boolean equals A and B, return A.compare to B equals 0. Oftentimes, equals is simply implemented like this. It's just hiding a call to compare to, if it's a comparable kind of element, or type of class. So I'm calling compare to twice, actually, and I only want to call it once. So that's why I'm going to do what the book does, and put all of this stuff in their own braces, not like that. And what I'm going to say is compare key to node.key. I know node.key exists because node is not null. Compare key to node.key. If r is less than 0, key is less, and I should look in the left subtree. If r is 0, they're exactly equal, and I can return the value. And if r is greater than 0, I know that key is more than node.key, so I should look in the right subtree. So I'm just going to use the same code as before. If r is, let's start with 0, simply return node.value. Else, if r is less than 0, go look in the left subtree. Else, go look in the right subtree. So this is exactly the same code as over here. Only difference is that they kind of did their fancy schmancy unnecessary formatting, and they look at these in order, just looks visually clearer on paper. But I think this is fine. So that's get. Get is the easy one. The real tricky one is to put something into the tree. Do I have enough time to put? Yes, of course I do. Okay, let's see. Contains. Well, contains. Well, let's think about it. Contains. You also have to walk through the tree. And the only real difference is that instead of returning value here, contains will return true or false. So I can write it recursively just like this. I'll need a second contains, but I'm too lazy to do that. So all I'm going to do is I'm going to say get key is not null. My contains simply calls this get routine, and if get returns something other than null, I know that the key is in the tree and I contains must return true. I'm just going to do it on a cheap. Oh, it's complaining. Why is it complaining? Because I call it key. This isn't cheating. I'm not causing extra work, much really, in fact, no extra work to write containers like this. In fact, I can write it a little better. If you really want to save one call, method call, you could probably say if root key is not null. And you don't have to go through the top get. You go immediately to the middle get, second get. But in practice, it will make no difference whatsoever. It's not less efficient. It's the same order of complexity. This is log n, because I'm always dividing by 2. This is log n, because I'm doing the same thing. Now, the tricky part is put. Now, put is tricky because, why is put tricky? You might just see what you have to do it from scratch. Put is tricky because, well, let's forget about that. It's just need to put things inside the tree. And I need to modify the tree. So, if I get down to an empty tree, and I'm told to put a mapping from a certain key to a certain value, I can create a new node. I'm told to put key and value, that mapping, the symbol table, added to a binary search tree. And I get down to an empty tree, or the tree is empty. I can create a new node. What do I attach the new node to? There's nothing for me. Where does a new node go? It can't go to root, because that means it will replace the whole other tree that already exists. So I have to be a little more careful. What I'm going to do is I'm going to write a routine that will insert a key value in the tree and return the new tree. I'm going to have a routine that inserts a key value mapping in the tree and it returns the whole new tree. So, put will be simple actually. It will simply say that insert into the root tree, the tree that starts at the root, insert key and value. And I know I haven't written insert, but this will insert this mapping into the root tree and return the whole tree. So if I give it root and there's already a big tree, it'll insert it somewhere in this whole tree, maybe at the bottom, and then it'll return the whole tree. So it'll return root to me. And what I'm going to say is root equals that new tree. So it may be that root itself stays exactly the same, and its left and right pointer stays exactly the same. But somewhere down the line, something will be different. Let's imagine the tree is empty, so root is null. Then insert is going to create a new node for the tree that maps key to value, and it's going to return that new node, which is now the whole tree. And I'm going to put that in root. So suddenly my root will grow by 1, it will be the whole tree. So let's do insert. Private. What does this insert send back? Let's find victims. That victims will be right in physics. What's your name? Yes. Nicole. Nicole. What does insert send back? What kind of thing? Your options are void. This is much part of this exam. The final exam, the final year at Stellenbosch, they ask you again about your first year stuff. I hope you guys know this. The final question, well, actually, if you open the paper, there's only one question. It's what does insert send back? It's much puzzle. And the options are A, void, B, no, C, key, D, value, or E, all of the above, or F, none of the above, or G, int, or H, Boolean. Look, you can't start cheating, you know. What do you answer? Get your degree. B. No. No. Why? Why did you pick no? Just a guess. Oh wow. What a lucky guess. Is it called right or wrong? Pass or fail? Pass. 4 people, 5, 6, 7, 8, 9, pass. Rest all fail. Nicole, I'm afraid this is a democracy. You failed your degree. And yet, how unfair? Because the answer is no. In search is going to create a new tree for me. It's in the same like that tree. And what is a tree? A tree is just a node with the left and the right subtree. So it's going to return some node. It may even be null, but it's going to return something. Insert. And this is the key, the tree that I already have. I'm going to call it tree. And I must insert a key value of key and a value of value. Okay, Nicole, you turn the page. There's one more question. What? Write the inside of insert. Where do we start? But that's not clear. What do you say? If I ask you to insert key and value in node 3, what would you do? Forget about all the show and the glamour, computer scientists. Okay, how do you write? It's okay, because I want to guide you to the right answer. So what about the following? How do you like this? There, I've put the mapping in the tree, and I'm going to send back the whole tree. It's a little poetry, or not poetry, what should we call it? It's a little literary crack. What do you think, Nicole? What do you think of my beautiful node implementation? I put the key in key, I put the variant value, I've added the mapping to the tree, and I sent back the whole tree. How do you feel about it, Nicole? What are your emotions? It's okay. Well, I can say that you're a very, very tolerant person, probably nice life, comfortable, low stress, nothing worries you, don't care about mistakes or anything like that. Ugly, sorry. Nicole, I'm sorry to pick on you, but you're such a perfect victim. What? No, because you don't know. I find something that knows the answer, it's always boring, because all the other class thinks, oh, that asshole. I can't interact people by asking them Socratic questions. So you don't have 5 minutes, probably it's like we have a papers. So Nicole, what's going to happen if 3 is null? If 3 is empty? Will that work? Why not? One word. That's 4 words. Well, 3 words. That's subtraction. It's increase. What if 3 is null? What will happen? It will return null. No, it's going to return null. Even if 3 is null, it's going to return null. As long before it gets to the null, return null, it will try to do this. It will try to do the key field of a null instance. And so the one word is not with the exception. You agree? If I try to put key, which is that parameter, inside the key field of 3, which is null, I'll get a null pointer exception. I can't put anything in the key field with something that's null. It's not pointing anywhere. 3 doesn't exist. It's supposed to be a reference to an instance of class node. I know that because I said that. 3 is supposed to point, reference, an instance of class node, but 3 is null. So there is no key field, it doesn't exist. There's no value field, there's no left or right field. So this definitely won't work if 3 is null. So let's add something special for that. If 3 is null, then I'm in a funny situation, because now I'm in a situation where I don't have a key. And I'm supposed to make this mapping from key to value. So what I'm going to do is I'm going to create my own new little tree. Node new tree is new node. So I'm creating a new instance of a node, and I'm putting it in the local variable new tree. And the constructor says that I can pass, damn it constructor, a key and a value. And this is still yellow because I never used it before. But look what happens now. Key value. So I call the constructor for node, I pass it the key and value, I create a new little instance of node that has key equal to key and value equal to value. Its left and right pointers will be null, because that's always how they start. And up here, this is no longer underlined in yellow because I've actually used it. Eclipse is telling me that, yeah, now you've used it. So I've got a new node that maps key to value. Its left and right subtrees are empty, they're both null, left and right fields. And this is my new little tree. It used to be empty, but now I'm going to return new tree. And new tree will be mapping key to value. And everybody's happy with that. I have 4 minutes to go. We'll speed up a little bit. I can't just do this, Nicole. This isn't right. It's just not right. And the reason is that tree may be a beautiful little tree that contains a mapping from 5 to some value. And now I'm overriding that previous mapping. I can't just put my new mapping in anywhere I want. I have to put it in exactly the right place. I can't override key and value like this, except in one case, and that is when key is equal to key. If this node says that, let's say, 5 maps to ABC, and now I'm asked to put into the tree a new mapping that maps 5 to DEF, I'm overriding my previous mapping. So if these keys are equal, then this is fine. Then you can replace value because I've now put in a new mapping in my symbol table. We did this before as well in the array. If we find an element in the keys array, you just assign the value into the values array. So I'm going to say here, if tree.key equals key. Now it's complaining again, but never mind. Okay. Now, a couple of issues. I can't say these are just equal. They may be the same key, but stored in 2 separate instances, like one string and a separate string are really the same string. So I'm supposed to use key.equals. Okay. I should compare the keys like this. But same issue as before, I really want to not call the compare to method too often. So I'm going to do it once, and I'm going to use the same trick as before. I'm going to say int r equals key.compare to tree.key. So compare the new key to the key that I'm currently looking at the top of this tree. And if r is equal to 0, that means these 2 keys are exactly the same, and I can just add my value here. Else. If r is less than 0, else. Right, only a few things to write. Okay, let's do that in more. Okay, r is less than 0. What does that mean? It means the key is less than the key in this tree row. So whatever's going on, this new key that I need to make value belongs in the left subtree. So I'm going to change the left subtree. I'm going to insert this key value mapping in the left subtree. And I know how to do that. I've got a routine for doing that. It's called insert. Insert into the tree's left subtree this key and this value mapping. So I'm calling myself recursively, insert key value to the left subtree. Now the left subtree may have changed, may be empty, and this will create a new little tree that contains key value mapping. Or it may have been quite complex. Whatever it is has been updated, and I need to assign tree.left equal to whatever this thing returns. Just as I did at the top, root equals insert root. It sends back the new tree, and I'm going to store that in tree's left. And the same for right. This last case is where r is greater than 0. That means key is greater than tree.key, which means key value mapping belongs in the right subtree, and I'm going to insert it there, and I'm going to assign that to the tree. Java is still not happy, man. What do I have to do? It says insert. It's not sending back anything in these last cases. So I've got to send back a new whole tree that I get after inserting key value into left and right. Okay, now I'm going to shock you a little bit. Well, half of you. I'm going to say return tree. Why do I do this? Why don't I return tree.right? I'm at tree. I've been asked to insert a key value into this tree, and then return the whole new tree. Just between you and I found out that the key actually belongs to my left subtree, so I put it there. I assigned this new subtree to my tree.left, but I'm still being asked to insert key value into myself and return the whole new self. So that's why I return the whole tree at the end of this. I insert my left subtree and I update my left subtree, but then I return the whole new tree. Okay, and in fact, return tree appears 3 times in all 3 cases, these branches of this if statement. So I can factor it out. I can actually only do it once. Okay, so now I'm going to stop. Oh, gee, I hope YouTube is still on. Yeah, it's kind of on. Excellent. Okay, oh, and of course, you didn't see that freezing, but never mind, YouTube won't miss that. I'm just going to watch that YouTube video. Oh man. So I'm going to stop here, and on Wednesday, I'll just finish this off if you come to class. Nothing special. And there won't be class on Friday. On Wednesday, I'll tell what's in the final exam if you want to write that. I'll give details about that. So if you don't want to come to class, at least watch the video if you're going to write the test. If you email me and ask me what is in the final test, I'll just say YouTube video. In fact, I won't even say that. I'll just say YTV, YouTube video, and you'll never know. All right. So now you know at least. And you, YouTube, I'm looking at you. Dad, give me a second. I can't see in the dark.